There is a common assumption about complex systems. For them to function, their operation must be understood.
That somewhere, a central authority must possess a complete model of the system's internal state. But this is not true. Many systems function effectively even though no single component has a complete picture of the whole.
To see how, let's observe a simple physical system, an assembly line for a gearbox. The process is divided into a series of distinct stations. Each station performs one specific action in a sequence. An assembly arrives, a part is added, and then the assembly is passed to the next station. The operator at each station is constrained only by their immediate task to process an input and produce an output. Through thousands of repetitions, the physical action itself is refined. Small variations are tried, inefficiencies are eliminated. An operator at Station 2 discovers that spinning a gear onto its shaft is faster than placing it directly. The official procedure gives way to a more efficient, learned motion. This is a local optimization. The output of Station 2 increases. Assemblies move through this single station more quickly.
The increased speed at one station creates a new pressure for the next. The system around it begins to adapt.
This new, faster procedure isn't recorded in any manual at all. It exists only in the muscle memory of the operator. That final spinning motion leaves the assembly tilted. To maintain speed, the operator doesn't straighten it. The output from Station 2 now deviates from its specification. The operator at Station 3 is now consistently presented with a tilted assembly. So to maintain the line's new speed, they adapt, learning to receive the part at an angle. This chain of adjustments propagates down the line. Each station adapts to the output of the previous one, which creates a set of unwritten, interdependent procedures. The line is now faster, but its operation deviates from its original design.
This adapted state is efficient, but it contains a hidden fragility.
The operator at Station 2 is replaced. The new operator, knowing only the manual, performs the task exactly as it's documented, placing the gear carefully onto the shaft. So the output from Station 2 now conforms to the original design. The assembly is passed to the next station in a perfect upright orientation. But the operator at Station 3, whose entire process is optimized to receive a tilted part, cannot handle the upright one. Their practiced, angled motions fail, the assembly fumbles. The failure at this one point cascades. The flow stops. The line has broken. And it wasn't triggered by an error, but by an action that followed the official procedure perfectly. The line's real-world efficiency actually depended on its deviation from the design. The increased productivity was never planned. It emerged as individual components solved local problems, creating a more efficient system than the one that was originally designed. But the same hidden dependencies that allowed for greater speed also removed the system's flexibility. It became rigid, optimized for a single unwritten path, and vulnerable to a component that followed the official design. The lack of central understanding was not a flaw. It was the mechanism of optimization. The system worked because no single component understood how it worked. And for the very same reason, the system failed.